for the today's topic related to the principal component analysis. So I'll be talking about first of all the theory into this particular session, and then we'll be doing a hands-on onto a Google Colab itself, making use of a Jupyter Python. We'll be making use of a Python, and then the Jupyter notebook will be making use of it for the further hands-on. So I'll start. I'll first give you an introduction of the principal component analysis. Then I'll talk about the need for the PCA. Then why to use the PCA, I'll be talking about. Then I'll be discussing a use case scenario and a real life analogy. Then I'll have the steps that will be used to implement the PCA. So along with the steps, the code you have to write it into the Python will also be demonstrated, and finally followed by the references. So I'll start with first of all, we were talking into the yesterday's class about that ML can be classified into supervised, unsupervised, and the reinforcement kind of a learning. So what we started into the yesterday's was the logistic regression, where we said that the logistic regression belonged to a supervised learning technique. So now the principal component analysis is an comes under the unsupervised learning, and it's a statistical technique that was introduced by the mathematician Carl Pearson in 1901. So basically what it is, if I see the definition from the book, it says that it's a dimensionality reduction technique. So I'll explain each of the terms into details, but I'll just summarize the definition, what the PCA definition as per the book says. It says that it's a dimensionality reduction technique that helps to find the correlations and patterns into the data set so that it can be transformed into the lower dimension. This is what the definition says. Now, there are three particular points to be noted into this particular definition. The first one is the dimensionality reduction technique. The second one says finding the correlations, and the third one says the finding the patterns. And then it says that transformation into a lower dimension. Now, the whole idea behind this lies into the curse of dimensionality. Right, so I'll be explaining like, okay, what is the curse of dimensionality, and then I'll try to come back to this particular thing. So if you see the figure, just have a glance at the figure where I'm talking about a one dimension, then I changed it to two dimension, and further I illustrated the same example with the help of three dimensions. So what example would I like to give at this particular place is, suppose that you are in a 1D plane and your coin has fallen somewhere into a 1D plane. So how much time it will take you to search that particular coin into a 1D plane will be very easy, because you define that it's of 100 yards and then you have to find out the coin, right? So finding a coin will be quite easy for you. Now consider a 2D, for example, consider a sphere of 100 cross 100, and then your coin is being dropped over there, and then you say, okay, how should I find the coin? So it means that when you'll be searching or you'll be trying to find it out into a two-dimensional space, your complexity will increase. Now consider a cube, right? So into a cube, which I can consider it to be a dimension more than 2, now you try to throw the coin, and then you try to find it out, okay, where's the location of the coin, right? So when you search into the 3D, your time complexity will further increase, right? So your computation time for finding the same coin, when you have to do it into a 1D, moving on to the further 2D, and then further moving on to more higher dimensions. So as we are moving towards the higher dimension, what we are trying to analyze is that it increases the computational time. So the higher dimensional data is usually complex. Why it is complex? Due to the inconsistency into the features that increase the computation time and that make the data processing and the exploratory data analysis more convoluted. So that is why the main idea is to reduce the dimensions. So suppose that we have a data set which is having, for example, 1,000 features, right? And now all these 1,000 features may not be as much responsible for finding out the analyzing the pattern, but then you have to consider those. So do you think that those 1,000 features should be incorporated, or you try to reduce the number of the features, right? So, because what you're trying to analyze is you're trying to correlate the features that were present into the original data set, and then final data set you'll be having a reduced number of features, right? So the increase into the number of the features will increase the computation time. Apart from that, it's difficult to visualize and it's difficult to interpret as well. So that is why the whole idea behind the PCA is to reduce the number of the features. So if you see to point number this one, that it works by transforming high dimensional data into a lower dimensional space while maximizing the variance or spread of the data into that particular new space, right? And how it is possible? It is possible through reducing the number of the features while information loss is minimum, right? So this point also needs to be focused, that much information is not being lost during this particular scenario, right? So that is why we reduce the number of the features while keeping as much information as we can for the particular analysis. Now, what is the need of the PCA? So since I was talking about, so what's basically is, it's about basically reducing the number of the features or the redundancy into the features and trying to find out highly correlated features. So what happens is, for example, if you see the data set at this particular place and assume that it's a small one, just to illustrate that, for example, the number of the features is 4 and the number of samples into the original data set is 150. Right. So if the number of the features is 4 and what you are trying to see is that some of the features among these may be highly correlated. So highly correlated may cause bias, right? So whatever output we'll be getting will be a biased one, right? So that is why what we want to reduce is, we want to reduce that bias. We want to get an accurate answers, and depending upon the highly correlated features, most of the times it will be prompting you a biased decision. In order to avoid that, and in order to avoid the redundant information, we try to find out the highly correlated features from that, and then we try to reduce the number of the features. For example, here you see how we reduce in original the number of samples was 150. In the new one also the number of sample is 150, but the number of features are being reduced from 4 towards the number of features being reduced to 2, right? So that is why there was a need for a PCA. Now, why to use the principal component analysis is, we use the principal component analysis to improve the visualization of data by reducing the dimensions, moving on from a higher dimensionality towards the lower dimensionality, so that it should be into an interpretable form, right? So, and to reduce the bias of the answers that we are getting into our output. Then it helps in eliminating the noise. It helps us to get uh, removal of the outliers or the relevant data, and thus it helps in data quality enhancement. Then highly correlated data is being transformed into the data into unrelated components, and thus it resolves the multi-collinearity. And also, when the example scenario for this is, for example, it can be used for the image data as well. So it's useful in data compression scenarios for text and images for the data transmission. For example, what we usually see whenever we are sending a image onto a WhatsApp, so sometimes we say, please do not send my image onto a WhatsApp. The quality usually deteriorates. So you kindly please either send me through an email or send me through another. If I'm simply talking about a general sharing onto a WhatsApp. So that usually the image is being compressed and then it is being transferred until and unless I apply some certain techniques in order to share it into the same format as the without the data compression was there. So we usually say, okay, please email so that the quality of the images should be intact. So that is why we can use the PCA for this data compression scenarios. Now, the use case scenario is, for example, we'll be illustrating this particular thing where we'll be taking an iris data set, and then onto an iris data set, we'll be demonstrating, okay, how many number of features in actually we had, and after the applicability of the principal component analysis, how many number of features, new features that we had are there. So this is just a use case scenario that we'll be presenting it during our demonstration session. So The real life analogy for this one is, I'll take two particular examples and I guess you'll be able to understand through this one, although one I've already given related to when we do a data image, sending of an image onto a WhatsApp. So the first one is summarizing a long book into a key points, right? So what happens is when usually we are getting ready for the exam and we just have 3 hours left for the exam, what we usually do, we do not refer to read the book completely, right? So what we want, we have some certain notes and we would just like to revise the complete syllabus into that particular 3 hours, and we just want to summarize the key points of it. Right. So a book may contain detailed explanations, stories, but at the core, the book is trying to convey few ideas. Right. So in order to summarize it into a page, one would extract the main theme and leave the irrelevant details. So for example, nowadays you might have seen that so I'm telling you side by side some particular live examples so that you can relate it. Okay, yes, whether this technique is used or some other technique can also be used, because you are learning a course onto machine learning where you are learning about all the techniques. Okay, so consider the generative AI tool. Right now, what happens is if you open a PDF, right? So that's a research paper, for example. So the complete research paper is with you, and sometimes what the scholars do is, PhD scholars usually used to do, and the masters also usually used to do this thing. What I have analyzed during my scenarios, they just tell the generative AI to give me a summary of that particular complete. It's a 40-page ASIM community survey paper, and they said that they have read it in one day. I said, I'm so surprised how they are able to read it into one day. Right. It took me so many days to read an ASIM computing survey of 40 pages, and they read it into one day. So I tried to analyze, okay, how they read it into a one day. They used the generative AI tool. They told, please give a summary of the paper. The complete summary of the paper was being summarized by the generative AI tool, and this is how they read the paper. Getting it? So although it's sometimes it's being useful, because sometimes we just want a gist of the thing, and in order to get a gist of the thing, these things would work. But if in case we are doing a PhD and then trying to use a generative AI tool for an async computing survey, is not a better option. So just try to relate that, okay, what particular technique might have been used in order to transform the complete book into a smaller summary kind of a scenario. And most of the times I also tried using it, and most of the times if you want a gist, it some of the generative AI tools are good at it, right? And they give you exact gist of or summarize the paper into the same way as you were expecting. Then compressing a high resolution photo without losing the important details. So the PC can be used for that particular purpose as well. You have a high resolution image which may need to be compressed for the purpose of the transmission. So all the important information is being kept intact, and you can use a PCA for this particular purpose. Now, these are the corresponding steps that are used to implement the PCA. So behind the scenes, since it's a statistical technique, right? So you need to know whatsoever mathematics you learned during your 7th, 8th class, or maybe 10th class. So some formulas needs to be revised if in case you want to understand and go into the deep core insights and the maths behind the principal component analysis. So the first definition that you would like to revise would be the covariance matrix. So if I'm not wrong, I guess I started it during 9th class or 10th class, the covariance matrix, right? And then into the 11th, I studied about the eigenvalues and the eigenvectors also, right? Then sorting them, selecting and doing a top K filtering on the top of that, right? So all these particular mathematics just need to be revised in order to implement a PCA, right? So I'll start with the step number. I'll first narrate on the particular steps. So there are particular 5 particular steps. The first one is the standardization of the data. So I'll explain into detail what do you mean by the standardization of the data. The second one is to compute the covariance matrix. Now, what is the relationship of the standardization of the data with the covariance matrix will be elaborated. Then further, we'll find or compute the eigenvalues and the eigenvectors. So first we'll compute the eigenvectors, and then we'll calculate the eigenvalues from that particular eigenvectors. And then we try to, the core aim is to find the principal components, right? Since the name is the principal component analysis. So the core aim is to compute the principal components. So we'll be computing the principal components into the next step, followed by we'll be projecting the original data onto our new axis. So we'll be trying to reduce the number of the features, and we'll try to find out the correlated features that were there into the original data, and we'll be transforming it into a new data with less number of dimensions. So here's the one. So if you see, the first one is referred to as the standardization of data, right? So what do you mean by standardization of the data, right? Consider simple movie rating data and see the number of the downloads that are being depicted over here. So now if you consider the rating is usually into the range of 0 to 5, right? So it's okay that, okay, I can move around 0 to 5, which is something within that particular range, right? And I can do that. Now, if you see the number of the downloads, right? The number of the downloads range from 100, suppose, to the range of 5,000, right? Suppose the range is so big that the number of the downloads ranges from 100 to 5,000, right? So despite of searching into this particular huge range, what the idea is, you try to scale it all the variables into such a way that they lie within a similar range, right? So the main idea of standardizing the data is you scale the data in such a way that all the variables and their values lie within the similar range. So how will you be able to do that? So there's a generalized formula stating that variable value minus mean divided by standard deviation. So it's based, the standardization of the data is you want to scale the data, you want to move the data around the number of the downloads, despite of ranging from 100 towards 5,000, you are trying to bring it into a similar range, and that is why you are trying to scale the data. And all the variable values will correspondingly be changed as per the formula. Z is equal to the variable value. So here, for example, it will be 1383 minus, you calculate the mean of that particular thing and you calculated the standard deviation. So minus the mean and then you calculated the standard deviation, you divided by the standard deviation, and that value will be replaced at by 1383. Similarly, for 668, you will be putting it 668 minus, you will be doing it from the mean, and then so you are trying to find and all the values within a similar range. So this is referred to as the step number 1, that is referred to as the standardization of data. Now the second one is you try to compute the covariance matrix. So once you standardize the data, now simple formula for the covariance is the covariance x comma y is equal to summation of xi minus x, the mean of x, yi minus the mean of y divided by the number of values minus 1. So that's simply the covariance between the variable x and y is being calculated, right? So the formula has been picked up as it is from the reference place, and we'll be using the same covariance formula for this particular purpose as well. Now, if you see onto this particular side, I have a covariance matrix is a matrix of, for example, if I'm having 2 features, it will be 2 cross 2 matrix. If I'll be working on to 5 features, then my covariance matrix will be 5 cross 5, right? So the first one says, for example, if I consider 2 features and I consider the 2 cross 2 matrix, so this is covariance A, comma A, right? Then is covariance A, comma B, then is covariance B, comma A, and then final is covariance B, comma B, right? So that's the values inside the 2D matrix. Now, what this particular covariance matrix is trying to do is, it is trying to express the correlation between the different variables into the data set, right? And if the value can be positive, the value can be negative as well, right? So for example, the covariance AA is 2.83. We take up to 2 particular decimal places and it says it's 2.83, right? And the covariance, for example, the value for the covariance A comma B is minus 1.23, right? So that's a negative covariance, right? So that's the correlation between the variables into the data set, and that value is being coming from this particular formula. So the negative covariance means it's indirectly proportional. So the positive covariance implies the directly proportional, and the negative value of the covariance implies the indirectly proportional among those particular variables or features that are available into the data set. Now it is essential to identify the heavily dependent variables. because they contain biased and redundant information, which reduces the overall performance of the model. So that is why you need to identify the heavily dependent variables that were existing into our original set, right? So it may lead to a biasness into our results, and we don't want a biasness, and it may lead to the redundant and the inconsistencies also. So that will reduce the performance of the model. So that is why we are using this particular step number 2. Now, once we calculated the covariance matrix, the next step is to calculate the eigenvectors and is to calculate the eigenvalues. Now, what are eigen? So, what basically the purpose of this particular step is, the particular purpose of the eigenvectors and the eigenvalues is that they are mathematical constructs that determine the principal components of the data set, right? So what we are trying to do is principal component analysis, and the step number 3 is determining the principal components of the data set through the mathematics or the statistics formulas, right? So eigenvectors are those vectors when a linear transformation is performed on them, then their direction doesn't change, right? And I repeat, eigenvectors are those vectors when a linear transformation is performed on them, then their directions doesn't change. And eigenvalues denote the scalars of the respective eigenvectors. Okay, so the eigenvalues are related to the eigenvectors. Now, what are the principal components, right? So what I said is the main goal of step number 3 is to use the mathematical constructs such as eigenvectors and eigenvalues to determine the principal components. Now, what are the principal components of the data set? Okay, so because the question arises, what are the principal components? So the principal components are the new set of variables that will be obtained from the initial set of variables. Okay, so we are trying to reduce the dimensionality. So the original set of variables into the original data set are being mapped onto the new set of variables obtained from the initial set of variables. So then they compress and possess most of the useful information. So the information lost is tried to be minimized that was scattered among the initial variables. So this is basically what we are trying to do into the step number 3. Now, further moving on, what happens is, okay, while I'm trying to determine the principal components of the data set, so will there be a single principal component? No, there will not be a single principal component. I'll try to find out the principal component 1, the principal component 2, the principal component 3, and so on, right? So what it says is that since you determine the principal components into making use of the mathematical construct, what is principal component 1? So first of all, the principal component 1 is the most significant and stores the maximum possible information, right? Similarly, the principal component 2 is the second most significant principal component and stores remaining maximum information, and so on. Similarly, if I go on to principal component 3, right? So the principal component 3 is the third most significant principal component that stores remaining maximum information, and so on. So if in case you just see that this particular is the direction of the most variation for the principal component 1. So this is what, and for the principal component 2, the direction of the second most variation is around this one. Now, what will you do is you'll sort. Usually we sort it into a descending orders, descending eigen values of that particular principal components, the new ones which we have calculated, and then we selected the top k eigenvectors, right? So we had PC1, PC2, PC3, PC4, and PC5. So we just select the top k eigenvectors from that. And finally, we are on to our last stage where we are getting the reduction in the dimensionality of the data set. So we are rearrange the original data with the final principal components, which represents the maximum and the most significant information of the data set. And finally, we get a data of reduced dimension. So that is what our aim was, to remove the curse of dimensionality, to find the highly correlated variables into the data set. And this is how we achieved it through the step number 5. So in the original data set, we had many more features. For example, 1000, we tried to reduce it, for example, to 50, right? So this is what we actually tried to achieve. through the PCA. Okay, so this is the transformation into the new axis, right? So if you see the new axis, so this is just a illustration for some sample data set being performed using the iris dataset, and we transform the original data into the new feature space defined by the top k eigenvectors. So here the two components that captures 95.81 of the total variation is being used. Again, we downloaded the iris dataset from the source, and then we uploaded it into the same way as we did it into our Google Colab yesterday, and we did a step-by-step writing of the code into the Python Jupyter notebook into the Colab. Okay. So this is all about PCA. Then maybe into the next lab session, we'll simply learn about the code of step number 1 till step number 5. So if in case you have any doubts, so what I can do is I can share the link of the iris dataset into the chat, and then you can download that particular data set at least, and you should be ready with your Google Colab. So those who haven't attended the yesterday's session or missed because of something should sign in to Google Colab before the next session we are going to start for the lab illustration. Okay, so I'll share into the chat box and you can download it. Okay, so that's all for this particular theoretical session. So I would like to invite, if in case any questions are there.
So participants, if you have any doubt related to the theory of this PCA, now you please ask. If it is fine with you, then you type clear.
Yeah, the use case, the sense current, when I mentioned about the real life analogy into that, I mentioned that yes, while transmission of an image, you can use a PCA for the purpose of the compression. I'm not saying which one is efficient and which one is not efficient. That then the question is just, can we use a PCA? Yes, we can use a PCA. Sense current, it's not about the conversion, it's just about the image transmission. Conversion can be to what particular format you want to convert. So conversion has a very broader term. Okay. So by now, I hope you are clear with the various unsupervised and supervised and some of the reinforcement. So sir, they are still going to cover for the reinforcement, and they might have covered by now the supervised and the unsupervised learning techniques, right?
Yes, ma'am. Only supervised and unsupervised machine.
Okay.
Reinforcement learning, no
Okay. So
session that.
reinforcement
Yeah.
is not there. Okay. Okay. Fine. Okay, I'll share the link of the iris dataset. Okay, I'll just tell one more thing that how you have to sign in into the Google Colab is you simply have to type onto open a new tab, simply write Google Colab, right? Click onto the first link, Google Colab. So it is, if it is the first time you are signing it, then use the same Gmail account which you are using, right? If in case you don't have a Gmail account, please create a Gmail account and then try to sign in, and then we'll be able to use the illustration for that. So the iris dataset can be downloaded from the GitHub as well as there is an inbuilt dataset from the SCI-Kit Learn, so we can use some sample datasets from that place as well. So it's not that you have to perform it only onto an iris, you can do it for other datasets as well, right? So since it's already available as a sample dataset, so we can use it at that particular place, but we'll try to import that particular library. So both ways we can do that. Okay. So then I'll be uploading it at that particular place from the Google Colab itself. Okay, sir.
Yes, ma'am.
Okay, sir. So we'll have the lab session at 2.
Sorry, ma'am.
Sir, we'll have the lab session at 2 o'clock.
Yes, ma'am. Yes, ma'am.
Okay. So if in case there are no questions, so
Yes, ma'am. So we can wind up the session now if they don't have any query doubt. So that we will start at sharp 2 o'clock for the next hands-on session on this PCA.
okay. Okay, sir.
Okay.
Thank you
Yes,
so
ma'am.
much.
Yes, ma'am. Fine, ma'am. Thank you.
Okay. Okay.
Okay.